Okay, for those who are just joined, so please scan the QR code for the attendance. Okay, I hope you hear my voice clear. Is my voice clear enough?
Yes, Professor.
Okay. All right. I think we can start the class. Okay. So I will go back to this QR code if you need one later. Okay. So let me go back uh, from the start. What we have learned from the first session last Friday. Last Friday. Um, we learned a little bit about calculus, especially about function, right? What function is and how we can use the function in our uh, mathematics equation. Uh, and then we learned something that I think important, that functions, you can represent the function with words, a table of values, a graph, or algebra, and so on. And you also learn a little bit about domain and how to set up the domain before you are move on to the next level. Okay, we then go to the vertical line test to check whether the equation is a function or not. Okay, so the vertical line test, you need to set up a line for x equals some number. That is for check whether it's a function or not. Okay. So before we talk about the inverse, we talk about the function first. Sorry, this is for the later part. So this is to check the function. Check function. Okay. And then we also learned that the functions we can have in a different set that we call piecewise defined function. Piecewise defined functions means the function itself, it can have several equations, right? So for example, this f, you can have as 1 minus x or x squared, but it's set up in a different interval. So you have like 1 minus x is here and x squared is here. So you can have more than one. You can have 2, 3, 4. It's up to you. Actually, you can make up that functions, because functions is actually, you can make any random functions by yourself, as long as you can check the vertical line, and if it is okay, then that's a function. Okay, and then we are going uh, learn about even and odd functions. We learn the increasing function, decreasing functions. I think we stop here, and then we go a little bit about some feedbacks from you. So this is uh, actually interesting. Some are positive feedback, some are negative feedback. I think because calculus already have been as such a difficult subject for the experience, right? Because when you heard someone like, oh, the mathematics seems not enjoyable because, yeah, I think it's a part of the culture. So I hope I can bring something new for calculus or for mathematics in general. But this is your feelings of calculus, and then this is your expectations. Yeah, I already read all of these feedbacks, and uh, yeah, I hope I can take this calculus or this math as you expected. Okay, as you expected in a positive way. Okay, in a positive way. Okay. All right. So we go back here. Okay, I hope you already scanned all the QR code. Okay. Okay, I will give you a few seconds to scan if you haven't. Okay, I think we can move on. Let's start with. Um, oh yeah. Okay. Let's start with. Okay. To check whether you got it or not. Okay. Determine whether the curve is the graph of a function. If it is, then determine the domain. So this is the first curve. Okay. So the idea here is to check the function, right? I hope you still remember. I'm just reviewing before. I hope you still remember how to check whether it's a function or not. You can type in the chat box if you want how to check the graph is a function or not. Yeah, vertical line check. Okay, good. Nice. So that is one way to check. So I think it's pretty obvious, right? If you check here, it's intersect how many times? It's one, two, three. So of course it's not a function. Right? Okay, the second one, how about this one? Now this is pretty easy, right? So if we check all the place here, it's exactly one, right? One time. So that is how you are going to check, right? So this is a function. Right? This is a function, right? And then how about the domain? Okay. Right. How about the domain? Yeah, you can check the point on the x for the domain. It start from here, right? It's around -2, and then it start here. It's 2, and look at this dot here. It's a close, right? So we need to include both numbers. So we can write this as, or you can write like maybe uh, in this way. Yeah, that's still okay. No, not a problem. And then do we need range? But if you want to check range, how many is there? We can check range from the y-axis, right? So here, and the max will be here. So this is 2. This is -1. So you can have -1 to 2. But I think the question is just asking the domain, so we just all right. Okay, so functions will be uh, it's assigning each x to exactly once or maybe I will write completely in a set of domain, in a set of domain exactly once, and this will be the result, will be the outcome, is range, right? Okay, I hope this is understandable for you, so you can easily understand. And then another thing about function, for example, if I'm writing x squared um, or maybe x plus 1, and then I have another one. Oh, wait. Here. Fx. Wait. Maybe there. Or maybe if this is, then yeah, I think this will be. Yeah, yeah, false.
Professor,
Any other
false,
idea?
false, false.
Yeah. Any other idea? Is it true or false? Well, sometimes you can argue, right? You can open discussion like, oh, because gx we have x plus 1 and then x. Oh, it's the same x, right? Oh, it's the same x plus 1. Yes, correct, Stephen, correct. Because you have this, so you have some restrictions, right? Some exception. So you can solve this, but it doesn't change the fact that it's still g. So g is still not the same as f. So this is actually not the same. Okay, because sometimes because you don't really uh, got the idea what the function is, you may go to this understanding. That's a problem because sometimes we forget what the function is. Okay? So the functions, even though if we simplify, we will be the same, it's still not the same in terms of the behavior, right? The math behavior, because it has exception here. Okay. But for example, if you have maybe here, so f, let's say I have function f. Um, is it true or not? This part, the f x and then gu.
True, sir.
True, false? Any
True,
idea?
sir.
Okay. One person say true. What about others? What do you think? Yeah, this is it's like how you make a conclusion, right? How you make a conclusion. So if you see here, okay, I can make out the x into the functions like this. And then g, when you put u, also make something like this. Then by looking at how the result is, then you can simply say that, okay, this is true. Okay, I think that's a little bit of function. And then let's move on to uh, some typical functions in the semester that you need to at least to check. Okay? I will not going like one by one explaining from the very beginning, because I think most of you already learned all these functions. Okay? I'm just reviewing a little bit and maybe which part that you might have forgotten. Okay, so first we are having the linear functions. Not really a problem, right? It's just a line. Power functions. Okay, so x with power of some numbers, right? X squared, x cubed, x fourth, x fifth, and then so on and so forth. And the root functions, right? Square root of x, the cube root of x, and so on and so forth. And reciprocal function is 1 over x and 1 over x with power of something. Okay, it's reciprocal functions. And I think in the very first chapters in limit, we will get into details about, and maybe uh, we will have this as an example. Okay? And then exponential, logarithmic, trigonometric functions. I hope you still remember. Okay, especially for the exponent and log. Especially for log, we will have a particular for ln. Okay, so ln is when b is going to be e. Okay? And then trigonometric functions, sine, cosine, tangent. I think this is very basic. Okay, and you need to remember how their behavior. Okay, so for example, in tangent, you will see this in this part. It will going for it's called the asymptote. I hope you still remember. It has the asymptote. Asymptote means it's a really long line that makes the curve in one side making into an infinite number. Okay, going to infinity. Okay, that's just a typical function that we will maybe going to discuss. Okay? The next thing that's still important is still in the functions. There is a subsection called transformation of functions. Transformation of functions. First is imagine the function is in the middle, the original function, okay, the f of x. Look at how the functions will transform when you move the functions. Just move, okay? Move to y positive. So I will maybe will use a green color. So move here, right? You just plus a constant. So this y you need to plus the constant. Okay. And then going down, right? Just minus the constant. How many points you are moving, right? And then this is I think most students forgetting the x-axis. Or sometimes if you're nervous, you will forget this simple things. If you move to the right, Okay. Then you need to have this x minus c. Okay. We move to the left, you need to have x plus c. Okay. Okay, don't mix this. Okay. Sometimes if you feel nervous, you will mix all of this. Okay, that's we call this move is a translation move. Translation. Right. Right. The other is still transformations, but it's not just moving, but you multiply the functions or you mirror the functions. Okay. So for example, this f of x, and then if you put the negative x, for example, it might resulting a mirror like this. Okay. If you multiply this c with the functions, you will multiply all the function and your function seems getting bigger, right? Like this one. If you divide with constant c, you will get smaller, right? But the proportions, okay? For example, if you see here, you draw uh, the proportion here, it's still looking similar, okay? Right? And the other part here is it's also mirror, right? But you mirror directly the y. Okay? So the y is coming the negative f of x. Here, the negative part is only this, the element x. Okay. This is not something that you need to memorize. No, I think this is quite logic. If you try to draw, and then if you want to check like if you understood or not, or maybe if you check whether this is true or not, you can try to just to make some function by yourself, maybe just x squared, and then you try by yourself how it looks like. If you are maybe multiply with 2x squared, how it looks like, or multiply with it half x squared, or even you can just make it maybe just linear function. But linear function, sometimes you will not see any curve change, right? Because it's just a line. So I think better if you want to check, you can check a simple one, maybe a quadratic function, okay, to check whether this is true or not. Okay? This is a simple check. Maybe in the exam, sometimes you need to make some checkpoint, and then an easy way to do that is imagine some curve, some graph. Okay? All right, that's transformations. Okay, the next thing is the inverse. Okay, what is inverse? So inverse function. Let me zoom in. Actually, this is yeah. I think I will only take the inverse for now. The other part like log, exponent, and then maybe trigonometry, I will discuss later after we break through the limit and the derivative. Okay, the first is you need to know what one-to-one function means. So one-to-one functions is, let me write first, and then maybe if you feel not really understand, I will make a simple explanations. So the function is called one-to-one function if it never takes on the same value twice. So if you have this, okay, this is, I think, the idea. Inverse. So whenever you find a function maybe like that. You see here, this is A, this is B. And this is y equal fx. At A and B, it has the same values, right? So A is not the same as B, but FA is the same as FB. So as a conclusion, this is not one-to-one, right? Okay. This line, this lining here is called the horizontal test. Yeah. So we have the vertical line to check the function or whether it's function or not, and this is the horizontal line to check whether it's one-to-one or check whether functions is one-to-one or not, right? Okay. Now, the inverse then, one of the requirement, okay, so the function has an inverse. Usually we write the inverse like this, f inverse. If f is one-to-one function, right? So, and this is pretty much the definition. Not really words definition, but if you say the inverse, if you check the word itself, it's like exchanging, right? Exchanging. What being exchanged, right? What being exchanged? The domain and range. That is the one that exchanges. Okay. So if so let f be one-to-one function. With domain is a, maybe let's write domain. Domain a and range b. The inverse has domain b and range a. And defined by for any y in B. So we can say for any y in B, because we already set up the definitions to be one-to-one functions, and we already checked the horizontal line, right? So we call this one-to-one. So it has an inverse. Okay, it has an inverse. So if you want to check whether the function has an inverse or not, check whether the function is one-to-one or not. Okay, just that. Okay. And then another thing, okay, if you see this inverse symbol like this, do not make mistake this as this is not the same as this. Okay, clear? Because sometimes students make this mistake, right? Okay, some example. Maybe I will just give you some easy, simple example. Then how we are going to use these definitions and find it with the inverse. For example, if you have the f of x is x squared, what is the inverse? Okay, my method, my personal method, because I think you have another method. My personal method, you see here, y is x squared, okay? And we know it's one-to-one functions because you already imagine that this is just this, right? But there is exceptions here. You will see later. So if you check this y equal x squared, what is the inverse? So to check the inverse or to find the inverse, because you know the idea that domain and range will be exchanging, then you need first to check to change the x and y. So if you see here, you need to make the equation of x, so it's square root of y, right? But this is not the end, because we want to make it in the inverse form. Then we need to write okay. All right. Okay, but you see, if you have this, it's kind of you rotate the graph, right? But you see here, not all domain and range exchanging, right? We are ignoring this part. So still, it's one-to-one functions within this domain. Here only. So whenever you find a functions like this, or maybe like this, the trigonometric, of course you will never get the horizontal correct, right? Because it has the same value, because trigonometric is over and over. But if you set up maybe setting up here, then you can have the one-to-one function, right? And then you can have the sine inverse, cos inverse, right? Tangent inverse. That's just idea on how you will get this, okay? Because we already set definitions that one-to-one, right? You need to have the horizontal test, right? But horizontal test, we can set up which domain that can be, right? So not in all domain it will be one-to-one, right? This is also not the case. Okay, do you understand up until here? Because sometimes oh, inverse is just us exchanging domain and range, but you need to make sure how it looks like visually, right? If you see here and then you say that, okay, the inverse will be like this, it will be a trouble here, right? Okay, we say this is square root of x, then this will be not logical, right? Not logically correct. Okay. Or do you have any questions? Or is it making sense or making uh, confusion? Is it make sense? Is it make sense or not?
Yes, Mister. Yes.
Okay, clear. Okay, so that's why, right? In the very early course, in the first week, I said domain and range will be important. This is one of the importance. Okay, so you need to set up which part that will be its domain and which part is not for to make the inverse. Okay. Mm-hmm. Okay. Why do you want to domain only on the left side? Not on. No, no, no. That's your thinking is wrong. Not 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 left side. But what you are see, what you will see. Okay. Um, Sometimes if you have, uh, can you draw the square root of? Okay, let me go here. Oh, because after this we are going to have the tangent and velocity problems. I will show you the GeoGebra, okay, so we can have some practice to draw the graph. So let me stop the presenting. I will go to okay, you'll see here, this is the GeoGebra. I already opened GeoGebra. Okay, let's draw. How to draw the graph in GeoGebra? You just click this for input. You can input any functions you want, but for now, let's just input x squared. All right. Okay, so this is our functions. Let's put another functions. Um, let's say the inverse of the x squared. All right. Now we are going to see the red line here, which is the square root of x. Okay. Now, if you look at, and if you rotate the red line here, if you rotate to the left, it will exactly making the left part of the x squared. Okay. Now the question is not about a left or right side. This part here, meaning the only way that the square root of x has a curve, right? Because below here, below the, if you make other line for this function g, then it will not possible because of the square root. Because square root, you need to have greater than negative, right? Greater than or equal 0, right? So that's why it's on only this part on the left that is rotating. The right part is not included, okay, for to making the inverse one. All right. Okay, I hope that's clear for Jordan. Okay, I hope that's clear. Okay. Mm-hmm. Okay, why does the minus y not disappear? It's not disappear. It is restricted. So we stop the domain only at the uh, only at this from zero to here, right? Yeah, from 0 to, yeah, infinity number there. Okay, so it's not disappear. We restricted the domain. Okay. OY is not negative square root of x. That's interesting. Negative square root of x. Okay, that's interesting. If we draw here another function, negative square root of x. Yeah, we all have this. We can have this part. But this negative and the positive, it can be into one functions, right? That's the problem. That's the problem. So the negative is also true. Yeah, it's also true. But uh, we can have this two into one function. Do you have you get it? So this red line and the blue line cannot have into one function. That's the problem. One to one via the graph again. Okay. Okay, one to one. Okay, see, let me make it disappear first. Okay, one to one. If you check the horizontal function, let me make horizontal line from here to here. Okay, so AB will be our horizontal line. So almost of all the point, we're making the same values, right? We're making the same values. So if we are going to have this x squared in a whole, then it's not one to one. Okay, it's not one to one. But okay, if we are just having the left part or right part only, okay. Let me go back to so I can draw one more time to. Let me go back to here, right? So if you have this, so it's not possible, right? That's why what I've said before, we can restrict the domain. So we can have at least two ways. First is this, okay, and the second is actually this, because someone mentioning about the negative, and the negative is also correct. It's also correct. It can be our functions. Yes, you can only just choose one because it has different domain. You get my point. The inverse f is both square root of x. Yes, but usually we are going just to choose the positive one because it's the general functions. Yes, both correct, both correct. So we set up our domain. Okay, we set up our domain. Okay, but usually in general, we just write that if we have this, then the inverse will be usually in general. Because if you write this positive, negative in one terms like this will be a problem. Why it's a problem? Because your domain and range is mixed. That's the problem. Okay. So that's why you can just write one here or here. Okay, that's also correct. All right, that's the inverse. The other way. Um, okay, I will skip the log and inverse of trigonometry. That will be our next when we deal with the derivative. I will go back to the inverse of trigonometry and the logarithm and exponent. Okay. Now, first, after this session, we will go to the limit. Okay. Or any other questions, maybe related to functions in the general transformations aside from inverse. Is there any discussion or maybe some questions from you? If not, then we will go to the limit sections. It's chapter 2. Okay, it's chapter 2. So tangent and velocity problems. Okay, let me go back to the GeoGebra. Okay. Wait. Let me do this. Let me move the line maybe here, around here. Maybe making B around here. So let's set up this. I think this is pretty much obvious if you have learned a limit before. What I'm going to tell you here is if we make a line A, B here, if we move A, if we move A and we make it getting closer to B, we will see there is a change, right, in the line. Or maybe I will make okay. Let me tangent settings. Let me change to maybe pink. Okay. All right. Now, if we move here, you will see it has a little bit of change in every point, right? Uh, okay, let me copy the graph first, and then we can move back to our notes. Okay. Let me put here. Okay. Okay. Okay, wait a minute. Sorry. All right. Now this is the tangent and velocity problem. So first we need to see the definition of the tangent. So uh, tangent means to touch or touching. So what does it mean for touch or touching? So we can say that like a curve, and then we have something here that touch a little bit touch here at that point, or there is something touch. So it will touching exactly 1 point, 1 point. Okay, at here is touching exactly 1 point. That's the precise definition of the tangent. Okay, and there's another definition also we call secant. A secant means to cut. Right? So if we see here, this A and B line, this is a secant line. So this is as terms, some terms that maybe you will find later. If you hear words secant, tangent, this is what it means. Okay, the secant line means that the line is cutting the curve. Okay, the tangent, the line, there's a line that is touching 1 point. For this case, it's touching at the A. Okay, hope you get the idea. That's the basically the definitions, right? Okay. All right. Okay. Um, let me make um, a point here. Let's say point P. This is at 1, 1. Okay. That's P 1, 1. Okay. So find tangent line of these equations at P. Okay, and if I'm using, let's say, let me make just another point here, Q. This is X and X squared, right? Q is just a random point, not really a point on exact number, but it's just a random. So I will make it as my variable X and X squared. Okay, so let's say this PQ is the one that we are going to check the value. So we can find the tangent. Basically, we find the gradient, right? The gradient. So gradient of PQ. So gradient, I hope you are not too confused about the gradient. So gradient and tangent, most of the cases is the same thing. Okay? You can say the gradient is, you see here, you see this y, this is x. You can make the gradient as a tangent, and like in the trigonometry, the tangent, or I mean, right, the tangent will be 1 over x, or the gradient. Most of the cases, that's the same thing. Okay. So what we are going to do here is we are basically pretty much we are making those approach. Okay. If you see here, we can have this, right, and also this, and basically we can make it as our triangle, right? So we can have, this is the delta. Okay. For y is x squared minus 1. The delta x is x minus 1. And then if you still remember, the equation of the tangent line will be, and this will be the gradient. Yeah. All right. Now, if we check, okay, if we check from here, if we check that if x is 0 from here, then the gradient will be 1, right? If x maybe 0.9, the gradient is going to be 1.9, right? If you check, and if you make it 99, right, your gradient will be 1.9. And if you check the x is 1.1, the gradient will be, if you use calculator, you will find, this is just to show you that there is a slight or a difference. Okay. Now we see that here it's pretty much, if you have 1, if you have 0, you get 1. You have 0.9, you have 1.9. And it's getting closer to m equal 2, right? So right in the middle, you have this 2. And from the left, you are going from 0 to something here, or maybe going under. And from here, you are going to have from 2.1 to 2.000001, right? This 2 is at the very middle here, right? And what I'm telling you here is basically the limit concept, okay? The limit concept that we are going to use in the future, okay? So all the calculus part, in derivative, in integrations, we need to make sure that we understand the limit. Okay? So if we are going to move this to move the AB line. Okay, so we move A going to going here, and then maybe we want to also approach B to A, right? We can approach from each side if you consider. And when it's getting closer, closer to something, it will reach the tangent part, right? Okay. Okay, let me make another uh, let me make another page here to make it more clear. Okay, this is the f of x, and let's say we have x here, and we have another point, and let's say we this is our a and b from the picture before, and let me make a line. Okay, that's the AB line, the second line. Okay, and this is the functions. This random function there. Okay, and let me make this h, the distance between x and just let's just say x plus h. Okay, now just by looking at this AB, we can make a triangle. Okay, all right. Now we know that this is the delta y and delta x. Okay, and we can write the gradient like this, right? Okay, and we can write the gradient in terms of the delta y will be, so let me write here is at point A here, this is f of x, right? And at point B here, this is fx plus h. Okay, so this is fx plus h minus f of x. Okay? And the delta x here, x plus h minus x, is just h, right? Okay, so I will just write h. Okay, now from the picture before, we know that, okay, if we move this a here, right, use the other color, maybe orange. So if you move a going here, approaching here, see my dot here, going here, going here, going here, and then eventually when it's approaching, getting closer to b, okay, the gradient here, or the tangent in this point here, if you see here, this is the tangent, it is going to be changed, right, in every point here, right? And eventually it will be approaching this b, right? Okay, and what is happening when you are approaching this point and you move this a going along this curve, dot, what is happening? What is happening is this h is getting 0, right? And that is why we can write here as limit h getting 0. Okay. And from what we have done before, from what we have seen from before here, when we are dealing with this, okay, it seems that when we approach from the left and we approach from the right, it seems getting closer to some number here, right? We are getting closer to 2 in this case. Okay, in this case, we are getting closer to this 2. But is it the same as 1.99999? It's not the same, right? Okay, that's the idea of limit. So even though 1.9999 is getting closer to 2, it's not the same as 2. Okay, got it? And you have the 2.0001. It's not the same as 2. Okay, but when we're dealing with this concept limit, this can be 2. Okay, do you get my idea, my point? Whole graph, which graph? The previous one, Blessing? This graph? Yeah. This part? Or both? Okay. This, okay, this is just an x squared. Okay. X squared, I have the second line, and then I have the tangent, and I can move the tangent going around the curve. Okay, and the tangent will be changing, right? Will be tangent. Okay. Okay. YH is approaching 0 here. The idea is I want to move my point, this A. This point A is here. I want to move this point, the green one. I don't have any green. AB. The second line is the AB one. Oh yeah, yeah, Laura. Oh, wait a minute. Okay, so when I move this point A, it will be going around this curve, right? Dot 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 dot. And when you approach B, you can say that it's going to approach this, right? Oh yeah, the green one. Yes, yes. Oh no, the black one. The green one is the curve. Okay. Okay, so when you are moving this A and getting closer to B, it means that my distance is getting closer, and we can say that the distance is getting 0. And I can say that in terms of limit, we can say that, oh, as limit h getting closer to 0. I haven't explained more aside from that. Okay, I will explain a bit more later. Okay, so we can write, if we want to make it getting closer to something, we can say limit. Okay, we can say limit getting closer. Okay, so when I said that in terms of number, we say this is, of course, is not 2, right? Or we can say this is not the same as 2, right? But in terms of limit, but in limit, it might be correct. So this limit, okay? Yeah, okay. In terms of limit, you can say that this 2 number it becomes the same. Okay, that's the idea. But remember, every time you're dealing with a limit, the actual number is actually different, the actual number. But if you are going into the limit concept, you can say it's the same. Okay. Okay. Hold your thought for a second. I'll move to another one, and I will make conclusion. And I think that will be more important for you. Okay. All right. Another thing that I want to make sure is okay. I think in the physics you learn that if you have the ball and you drop a ball, right, and then maybe it's telling you that find a velocity. Maybe after 5 seconds, if you have the distance equations. Oh, this is the distance equations, 4.9 t squared. This is from the Galileo Galilei experiment. Okay, how you find the velocity? You remember the average velocity is change in position divided by how many times elapses, or time elapsed. Okay, but the time is just 5 seconds. We need to know the interval time. So what I can do here, oh, probably let's say we have 5, maybe first to 5.1. So we have 0.1 change in time. Okay, so let's say that is true for our subject here. So we can plug into our equations 5.1 and 5, and divide by 0.1, the difference in the time. If you check uh, the calculator, it will be 49.49. Okay. Okay. Let me move here. New one. Okay. So you check 5 and 5.1. You check again the interval at 0.1. You check again. This is meter per second, and you get another results. Okay. Oh, okay. We check again. Let's make the interval time getting closer. Let's check 0.0.1. Okay. And you can check this if you want. Make more zero in your calculations. Let's say 0.00001. In conclusion, as the time closer to 5, you can also check the 4.9 if you want. So if this 49999 or 5000001, that is the one that is closer. So imagine this let me move right here. It's actually, this is, let me write here, very small. This very small. Okay, even maybe the actual is just, it looks like like one line like that. And sometimes you cannot even differentiate between those points. Okay, but just imagine, this is very, very small. So 4.99999 is really, really small. It's really, really close to 5, but it's not 5, right? But from here, as t closer to 5, okay, let me continue here. As t closer to 5, average velocity is closer to 49. Okay, but it's not 49. But if we use limit, we can say it's 49. And the terms here, when it's happened, this happened, it's called the instantaneous velocity. Okay, what does it mean? It means the velocity at exactly at that point. Or here, if we are going to look at what we have done, let's say that. So you want to know the tangent on point P. We can say that this is the instant, okay? Or let me write here. So this is A, B, and again, you are going to change. There is rate of change, okay? There is a rate of change. So we can say that there will be an instant rate of change. And this will be related to limit and derivative. Okay. Okay. Then the terms, okay, the terms for limit. Okay, there's some terms for limit. If you have limit, okay, as x approaching some number, okay, of a function, you can say that this is just a constant, a finite number, okay? Like we have done before. We can have 2.0001 or 1.99999, but we can make a conclusion that is 2, but we need to make a new concept, okay? So limit is a new concept, or a concept that make or not make, that utilize, okay, utilize infinitely little in numbers. Okay. And later you will see we are going to have dx with the derivative, ddx, we have integrations, blah, 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 dx, right? Why we are writing those dx is because we are dealing with the limit, okay? We are dealing with the limit first. All right. Okay, now I think still I need some graph to check with you, okay? To check whether you got my idea or not. Okay. Let me go back to the GeoGebra. Okay, let me delete all here, and let me change my function and make it let's say we have x squared minus 1. That will be our function now. Okay. Okay, we have x minus 1 over x squared minus 1. If you plug in this function, graph in the GeoGebra, is there any anything that is weird? Okay, what happens when x equal 1? What happens when x equal 1? What
The
is happening?
function is undefined.
Undefined, right? It should be undefined, but why GeoGebra showing me like this? Anyone have an answer? It's related to limit. Okay, so it should be undefined, right? But let's check here. Let's going into this point 1 and see what does it mean, or what is the numbers 1 assigned for in this function. It's assigned for 0.5, half, right? What does it mean? Oh, is it, which one is wrong? Our function or the GeoGebra is wrong? It seems weird, right? Because we know that it should be undefined. There shouldn't be any line, right? But remember what I've said before. If we look back, okay, at the what we have done, 1.99999 and 2.0001 is really close to 2, right? And you can say that, okay, we can say in limit it's 2, but in reality, if we zoom in, okay, this is take quite a while. Check, zoom in, zoom in, zoom in. Wow, it's still like a good line, right? Checking. Wow, it's still good after all this time. Okay, yeah, it's quite a few times. Still checking good. Okay, can you see any displacement? You see it?
Yes.
Okay, that's what I mean. In limit, everything is really small. The gap is really small. So when you draw the line, you will not see in real life, because GeoGebra, it has some computations for drawing the graph, and it will be drawing like 1.1 point. In real point, the dot, right? But when we draw in the paper, in your book, in your notes, you will draw exactly at x equal 1. You will draw like a open dot, right? Okay. Let me go back to the notes, and I will show you what we are usually drawing when we are still in high school, or maybe when we are learning the limit concept for the first time. Okay, so for the first time, we let me make this. So usually we are having this open dot here, right? Because probably because our teacher says so. Okay, there is a an open dot because there will be undefined. Um, the function will be undefined on that point, right? But when we draw in the real world calculations, real world engineered graphing visuals, sometimes you will not see because of the limit. Okay, so what does it mean is actually when we deal with limit, we deal with the concept that's really small. Actually, it's not infinite, but I will write some quote here to make sure that what this means is really, really small. Okay. So, what is our functions before? Functions is x minus 1 and x squared minus 1, right? So let me write at x equal 1, fx undefined, right? But, okay, if we write limit as x approaching 1, this is, okay? Do you understand? Do you understand the concept? If we just use the number and plug in the number inside the functions, we will be undefined, right? Because it will be 0 over 0, right? It's undefined, or we can say it's indeterminate form, but I will not explain late in details for now. Okay, but for now you just say it's undefined. But in limit, if we are going to through this concept of limit, we can have the 0.5. Okay, so this will be true even though if fa is undefined, it's still true. Still true. Okay, still true. Okay, okay. Do you have any trouble to for this idea? You got it? Okay. I hope you get the idea of limit. Okay. So limit is a concept. Okay, limit is a concept, not really like oh uh, I'm looking at some formula. No, no, no. Let me go back here. This part here is still continue, okay, but I will continue this later. Okay, this is the part that you are familiar with, right? I will continue this later, but for now, for limit concept, I would just say that okay, we have this limit, and this limit means we are saying that something are close by, really, 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 really close, and we can have that as a number, an approaching number, and we can say that this is true in a limit. Okay. Okay, I need one more slide to check with you. Okay, this is just how we are going to approach, okay, why we need limit, okay, why we need limit concept to go for the derivative and integrations. I will start by the triangle. If this is the base, this is height. The area of triangle is, of course, it's just half base times height, right? All right. If we have a circle and we make the triangle inside the circle, and let's say this is A, B, and O, okay? And we have, let's say this is, let's mark this as our height, and AB is our base here, okay? And if we are looking at their circle, then from the center point to some, this will be our radius, right? So our radius, the center point, let's say P, AP is having R, OP also the same radius with OP, BP, AP all the same radius, okay? We call this, let's say this is a polygon with n equal 3, which means the sides, okay? All right. If, okay, if you remember, or before that, let me just continue here. So polygon with n equal 3. Let's increase the polygon. Increase the n, the number of n for the polygon. So the sides will be more and more. So n equal 4, n equal 5, 6, 7, 8. Let's say we have 8. The n is equal 8. So let me draw this. So yeah, 1, 2, 3, 4, 5, 6, 7. Yeah, it's 8. And this will be the polygon. The polygon oh. Okay. Okay. Okay, imagine from these sides of 3, it's 1, 2, 3, and then you have sides of 8. Okay. 1, 2, 3, 4, 5, 6, 7, 8. And imagine you increase more and more sides. You will see that it's eventually getting closer to the circle itself, right? You get my idea? Okay. So let's see here. So when n is equal 8 here, the total area okay, remember that if we are having this A, B, O, and this is having the H, okay, this is the same triangle as this ABO at the first, at the n equal 3. So the total area for the ABO only will be half ABH. And then you multiply this because it has uh, 1, 2, 3, 4, 5, 6, 7, 8 triangle. It has 8 triangle. So you need to multiply with m. So it means 8 triangle. Okay, as n getting larger, what will happen? Do you see here? This is the radius, right? Look at the radius and the height of the triangle. Imagine, okay, imagine from here, from this height, okay, from this height here, and this radius. So when it's getting larger and larger, the n is increasing, right? The n is getting larger. What happened with the height? It's getting closer to the radius, right? The length. So the height is, or getting closer to r, right? So what will happen? So we have half AB n, right, and h. Eventually, if we are using the limit concept, or maybe just imagine not including limit, imagine just getting closer, and then we can have that this h is getting closer to r. And what will happen in this ABN? It will be getting closer to 2 pi r. If you remember, the pi is actually the ratio between the circumference divided by the diameter. Okay. So you look at here, the AB here, it will be getting closer here. So the AB is eventually will be getting closer to this circle, right? And that's why it's getting closer to the circumference, the ABN, okay, the ABN, multiply with the sides, the n, and then this half, and then that's why you get it's pi r squared. So actually, the limit concept can help to um, prove some geometric problem, geometric formula. Okay, like area, volume, and etc. This is just one example. Okay. Okay, I hope you don't get confused on this one. In this one. Okay. All right. What else we have? Okay. Maybe to close this limit, uh, let me write the definition. So if you have limit as x getting closer to a, okay, the function is defined when x is near or close the number a at some open interval uh, except, okay, except maybe at a itself. Okay, what does it mean? It means that maybe f a is not L, but still the limit is true, even though when you plug in the limit, it's not the same as L, as the number, like the number 2 before, okay? Or the undefined one, the x equal 1, right? The L is half, okay? Okay, this is the pretty much the definition for today. All right. Okay, any questions first? Any questions? Any questions? I hope you get my point, even though I know I've make some reference for, and maybe we are going on circle, but I hope you get my point. Okay, I hope you get my point. Okay, when you understand this point here, I think we will getting better. We'll be getting better. Okay. Okay, if there's no questions, okay, let me ask questions and let's have some small feedbacks. Okay. Okay, are we ready? Please prepare your smartphone. Maybe paper and pen if you want. Prepare the smartphone and also paper and pen. Actually, if you don't really need paper and pen, that's still okay. I think not really much calculation, but I think better if you have paper and pen. Okay. Okay, are we ready? Okay, are we ready? Okay, let's. Okay, OMG, scan the QR code. Okay, we are waiting. Increasing 17, 18. Okay. Okay, wait a minute. Okay. Waiting. I think already half. Okay. Still waiting. So in the meantime, you can check whether you have paper or not, and maybe pen, or maybe a tablet if you have a tablet. That's good. Okay, 33. Okay. Uh, if you have difficulty scanning the QR code, you can go to dementi.com and type. Okay, you can go to dementi.com and type 4746241 if you have difficulty getting inside the system. We are still waiting. I think we have around 9 to 10 more students. Yeah, eight more, eight more. Okay, ready. Okay, now it's 47 more students. What do you mean, Jordan? You mean the which part? Yeah, that's the limit. Yeah. Okay. Okay, let's uh, okay, let's start in a second. Okay, ready? Okay. Uh, there is no time limit for this one, but there will be in the other in the other part. Okay, which of the following statement is false based on the picture of function g? False. Okay, false. Okay. All right. Okay. Okay, be confident. If you see your friends going for some answer, maybe that is wrong, maybe that's true. We are not sure, right? So check by yourself. Okay. Good. All right. Okay. Blessing, that's okay. Okay. All right. Okay, let me give you 20 seconds more. 20 seconds. 20, 19. Okay, 15 seconds. 15 seconds. Okay, waiting for a moment. Yeah. Okay. Let's see. Okay. We go for another one first, and we can check later. Okay. Uh, okay, get ready. Answer fast to get more points. Okay, good. Whoa. Who's the fastest? Oh. Okay. Okay, good, good, good. Alan, good, good. Number 2. Okay, ready? All right. Oh, good, 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 good. Okay. We'll get faster now. Oh, Casper. You get most of the points. Okay, most of the points. Good, good, good. Okay, thank you and see you again. Okay, thank you and see you again. Okay. The answer for the previous, the multiple choice, it has 2 answers. Okay, it has 2 answers. The domain is false, and the values for the -4 is wrong also. Okay. All right. Uh, thank you for your time, and see you again next time. Okay.
Thank you, Professor.
Yeah. You're welcome. You're welcome.
Thank you, bro.
Okay.